Welcome. Today I want to talk a little bit about graph coloring. It was a project I have started with in 2014 with Jenny Nitishinskaya, and at that time I'd been interested already in discrete manifolds. These are special graphs, and I wrote you the definitions here so that I don't have to write too much on the board additionally. And these discrete manifolds are graphs for which every unit sphere is a discrete d-1 sphere. D-1 sphere is again defined graph theoretically. The D sphere is a d-manifold such that if you take away a vertex we get a contractible graph. So that's an example of a two-sphere, and at that time I had the impression that it should be easy to color manifolds. Coloring problem, especially the four-color problem, you can already play with when you're a teeny little kid. And so these are some blocks here, and we can ask, for example, to arrange these blocks in such a way that no adjacent or touching blocks have the same color. So I start here doing that, and I cannot put the red here, I have to put the blue, I cannot put that here. So you see, kind of have a little bit of difficulty here. So if I'm not careful, I cannot put the green one here. And one of the ideas you might get, and that's actually the SAR idea, is look at level surfaces. And what you do here as a tiny little kid, what you do is you color it with what one calls Kempe chains. So I take the red, blue, red, blue, red, blue, I just put them. This is easy, kind of, that's kind of what I do. Then I take the green, yellow, green, yellow. So now I don't have problems with green, yellow, green, yellow. So, and then again I take a red, blue, red, blue, red, blue, and so on. So I'm actually out of thing, and then I'm doing again the red, the green. So that's the idea. Maybe I have to shift it one so over, and now I have four-colored this thing using this idea of using layers to color this with two colors. These are Kempe chains, and Kempe chains are a wonderful tool. They have been introduced by Kempe in his attempt to prove the four-color theorem, and the proof still survives as the five-color theorem. You can there's an easy argument using this Kempe chains that you can color every two-sphere or every planar graph with five colors. Now I prefer to stay completely into discrete, not assume infinity. So I'm taking affinities point of view. So we only look at graphs, finite simple graphs, and also the notion of planar. You know, planar graphs are graphs which you traditionally you can draw in a plane, or equivalently you can draw them on a sphere. These are planar graphs, and but this involves Euclidean space, and we don't want to involve Euclidean space because it might just not exist, right? The axiom systems might just crash at some point. Also, I'm pretty sure that everything you can do in mathematics you can do with a finite with a finite setup. I'm not a Brouwer intuitionist, but I think it's just better if you, in a combinatorial setting, stay within a combinatorial thing. So what we have to do is we have to color planar graphs in for the four-color theorem. It's an interesting, famous story. It's told in millions of books and papers. What I prefer is to look at it in a geometric way. So what we have is we have a manifold like a sphere, and we want to color it. So manifolds are kind of easier to understand because you have kind of locally you have just again manifolds as boundary. And in this case it's easy. For example, this manifold can be, it's easy to color it, so you color that, and then you can color also this side, and then you can use this Kempe chain idea to color here alternatingly with different colors. So I make it yellow, yellow and blue, yellow and blue. You see, this was not possible to finish. We cannot put another yellow or another blue here, so I have to use another color. I have to use a fourth color, and that's why we need four colors in general. And it's clear that it depends on the parity, right? Whether it's even or odd. So this we can color with 3 colors, because we can just put 2 colors on the boundary and 1 color in the middle. And this one, for this one, we need already 4 colors. And when you put them together, you make a planar graph. You have always, we can always use only 4 colors. I will tell you kind of why this is true at the very end. So there's a kind of an argument which tells you, you know, that has to be true. It's not that you have to go with a computer and look at thousands and thousands of examples and just check it. That's not insight. So that had been the introduction. So first of all, I want to talk about the problem. What is the maximal? Now this is a very interesting question, and already in the case d equal to 1, it's kind of interesting that the parity matters, right? In the case d equal to 1, if you have a one-dimensional graph, which has to be a cyclic graph. For a cyclic graph, right, so we have for a cyclic graph here, it's 2, and for a, we need 3 colors. So d is equal to 1 is no problem. For d equal to 2, we have already kind of an interesting question. And I must say, I was completely intuitively wrong with my feel that coloring manifolds is easier than coloring 2 manifolds is easier than coloring a planar graph. And the reason is this theorem of Whitney, or goes back to Whitney, which we are going to look at. But let me just tell you a story here. I thought at that time in 2014, every 2 manifold has chromatic number 4 or less. And I suggested actually to Jenny to prove this using this idea of using level surfaces, this SAR idea, and then on the level surfaces use kind of some kind of Kempe chain idea. So we had a first meeting, and I explained her the strategy of the proof. She wrote down a graph, and I show you this graph here or here, which is a 2-dimensional projective plane. So every unit sphere is a circular graph, and it's definitely a 2 manifold. But for P is equal to P2, right? So in this case, we have already 5 is possible. And it's a very interesting graph. I could talk about for a whole hour about this graph, because if you take 1 point away, you get the Möbius strip. And this Möbius strip is completely flat in the sense, graph theoretical sense. So all the curvatures are 0. If you add the additional point, then the curvature at that point is minus 1/6, and there are 7 points which have curvature 1/7. So the total curvature is 1, because it's the Euler characteristic of the projective plane. So it's very interesting also if you take 2 such graphs where the vertex has been removed. That's no more a sphere, it's no more contractible. And the sphere has to have the property that if you take away 1 vertex, then it becomes contractible. So if you take this vertex away, it becomes contractible. Why is it contractible? Because I can take away this, and then it's contractible. Why is this contractible? Because I can take this away. Why is this contractible? I can take this away, and so on. I can take away more and more until I have 1 point left. And that's the meaning of contractibility. A sphere has the property that if you puncture it, then it becomes contractible. That's the definition of a sphere. Now this projective plane of Jenny, this is not contractible if you take a point away. Indeed, it's actually it's a Möbius strip. It has Euler characteristic 0. It is a beautiful surface. It has 0 curvature everywhere. And if you glue 2 of them together, you get the Klein bottle, which is completely flat in the graph theoretical sense, like the Clifford torus is completely flat. It's Euler characteristic 0. It's very, very a beautiful graph, and it shows that you can see that the chromatic number is 5 because the Möbius strip has chromatic number 4, and so you have that. You can just check it. So this was very embarrassing for me to, we have made a proposal for a summer project, and then in the first meeting already that whole thing has been crashed. But still it became very interesting because we looked at cases like higher genus cases. And so what happens is you have a higher genus case like the donut. What happens is there are monodromy things. So you actually, it depends kind of how the length of the minimal geodesics, etc., they have to be even, or this determines how you can color it, how many colors you can color it. So in most of the cases you can do it really with 4. So I was somehow right that in general you can do it with 4, but there are examples with 5. Fisk example. I can show you the example of the graph which Fisk took. So this is a donut, right? You take that together, you get a donut. And then what he did is kind of, you can do that graph theoretically. I show you a donut. This is a 2-manifold, discrete 2-manifold. Every unit sphere is a circular graph. But what is done in that Fisk example, it's done in such a way that you twist it a little bit. So that's called a Dehn twist. So you twist it a little bit. You have points where the unit sphere has 5 elements. So you need 4 colors here, 4 colors here. And then you have a path, like a Kempe chain, which goes from one to the other, which makes it impossible that you can mend it. And so you are forced along this path to use this coloring, and then you will get to the other point. You have a problem. So you have this non-simply connectedness allows you to force a higher chromatic number. And then Albertson and Stromquist, they actually show that if the torus is big enough, then you can do it. So smaller than 5 under some conditions, smaller than 5. There is no example known of a 2-manifold where the chromatic number is 6. In general, for a d-manifold, the chromatic number should be smaller or equal than 2d plus 2. So the minimal coloring, that's very interesting. How do you do that? So the minimal coloring is a condition which you have to kind of check. So if I'm taking this and I'm coloring one tetrahedron with 4 colors. For a tetrahedron, I need 4 colors already. So I take 4 colors here. And what happens is, so I need 4 colors for a tetrahedron. Like for a triangle, I need 3 colors. So I need 4 colors. Now what I can do is I can take this tetrahedron and flip it over one of the sides. And what happens is that forces, and I can take then the color here. I can then take this color here. Now I'm continuing like that. And I take this tetrahedron here, I flip it on the other side, I get it here. So in this case it matched up because the cardinality of we had to go 4 times around because that was even. We were able to do that with 4 colors. So we could, this is what I call Eulerian. The reason is because in 2 dimensions the analog is that every vertex, for 2-sphere, Eulerian means that every vertex has even vertex degree. Analog here in 3 dimensions, that the intersection of this unit sphere with this unit sphere is a circular graph, always, because it's a unit sphere in the unit sphere. So it's always a circular graph, and if that circular graph is even, that we call that Eulerian. So if you have a 3-manifold which has this property and simply connected and has this property that every of these intersections of 2 unit spheres is even, then you can color it with 4 colors. That's something which goes back to, I think Hewood has kind of seen that. And that's, by the way, also the reason for this 2d plus 2. What you do is you take the manifold and you color a maximal simplex with d plus 1 colors, and then you go and color everything kind of what you can. Sometimes you get constraints. If you get to a constraint, you just put a d plus 1 completely different colors. And so this kind of breaks this constraints. That's a pretty bad upper bound. You know, we think that it's lower. So in the case of d is equal to 2, so that would give you 6. So for 2 manifolds, you have a upper bound 6 colors. And in the case of spheres, you can do it with 4. That's the 4-color theorem. And in the case with, in general, we need at least 5 here. We don't know. We have no example of a 2-manifold with 6. So never look at embeddings in Euclidean space. Euclidean space don't exist for us. So this is a poorly combinatorial problem. D-manifolds we find like this. What is the chromatic number of this D-manifold? How high can the chromatic number get? And what you have also in the sphere case. How high can it become in the sphere case? So in the case d equal to 2, we deal with a discrete 2-manifold. And we have seen that for spheres, the chromatic number is more or equal to 4. And the reason is that two spheres can be characterized as graphs which are maximally planar and are 4 connected and have more than 5 elements in the vertex set. So let me just explain that briefly. So first of all, the notion of planar, that seems to be involving Euclidean space, but there's a theorem of Kuratowski which tells you can define this purely combinatorially. Planar means just that there is no 1D barycentric refinement of a K5 or K33 which is embedded in the graph. So I have you here the K5. The K5 is a 4-dimensional simplex, and the K33 is the join. We will talk about the join in a second of P3 point graph P3 with P3. These are two graphs which cannot be embedded in a plane, as Kuratowski has shown. But as affinities, we are not interested in the theorem of Kuratowski. We are interested in definitions which make sense in a combinatorial sense. And the definition of planar can be done purely combinatorially. And this theorem, which is a proposition which is essentially due to Whitney, I did not see it really in this form, but I proved it in 2015 around that first paper on topological graph coloring. In order to show this equivalence, what you have to do is you have to take a two-sphere and then first of all show that it's planar, and then it's maximal planar. Maximal planar means that you cannot add another edge. But if you have something like that, and say you wanted to add an edge here, this is kind of clear. What happens if you add another edge here? What happens is the unit sphere of that point here is no more a sphere. Clear that it has to be maximally planar. Also 4 connected. Stromquist, who wrote a nice thesis in '75 here, I think it was under the guidance of Gleason, about the 4-color theorem. That was this kind of works have been completely overshadowed by Appel and Haken proof, right? It is computer-assisted proofs. And but they were actually very close here. Also, Fisk has a topological approach to graph coloring, which is very interesting. And also this didn't pay, once you had the proof, this was no more kind of considered so interesting, which is a little bit a shame, because we don't like in computer assisted proofs, because they don't give you insight. I believe in the proof. I mean, it's something which has been done again at least 2 more times. Others have rewritten the programs, and it seems to be a solid proof. You can accept it with the same confidence than any human proof, but you don't get insight why it is true. Now, in general, so we don't know whether this is a conjecture of Albertson and. Maybe I'm bending here a little bit because they didn't work with this exactly, with these definitions, but they probably are. It's probably equivalent. This story of the 4-color theorem or coloring theorem is very, very treacherous. So people have made mistakes again and again and again. I should have put that maybe in the previous part. There are some cases which are easy. If you look at algebraic operation. So first of all, you can take the Cartesian product. It's quite an interesting thing. How do you define a product which remains in the class of d-manifolds? And so what you take is, if you have A and B are manifolds, it's subgraph here, complete subgraph here, you just take all these pairs. That's not the simplicial complex. This is the simplicial complex here, all these simplicity. This is not the simplicial complex. A cross the K1 is the barycentric refinement. The point is for this thing, so the chromatic number A cross B is a d-manifold. The coloring is the dimension. So the dimension functional on the simplices is actually a color. You have in a 3-dimensional graph, you have tetraeder. Tetraeder, you need 4 colors, right? And for a 5-dimensional graph, you need 6 colors because there are K6 inside. Now there are other operations which we can do. We can take the disjoint union. That's an addition. But then dual to the disjoint union is the joint. A and 2, B and 2 graphs. A plus B is the joint. So it's a Zykov join. For example, you have a P3 plus P3, this is K3. So that's the utility graph. So that's what we have there, kind of just as a constraint. So what you do is you take A and you take B, and then you connect every point of A with every point of B. You take the disjoint union, and then you connect everything here with everything. The unit sphere of a point in A plus B, of a point A, that's nothing else than SA plus B. And SA plus B is A plus SB. Now, because the unit spheres are spheres, and this is a sphere, by induction, these are spheres, just dimension lower. S of B is one dimension lower than that sphere. That's the proof that the join is a sphere. So if A is P and is Q, then the chromatic number of A plus B is P plus Q. So the chromatic number, it's compatible with the addition. If you have one graph and you color it with P colors and this graph you color with Q colors, now you leave these colors but take them differently. So you have P plus Q colors. But now because you connect everything with from here to here, there can be no collision with color, so you cannot kind of get away with less color. It's somehow strange. I missed this for a very long time. The consequence is, for example, the chromatic number is 6. So I actually, even in some of papers, I have speculated that the D sphere should have chromatic number D plus 1, that's the minimum, or D plus 2. And that's completely wrong. So if you take C5, that needs 3 colors. We have just seen that. The C5 needs 3 colors. And you take another C5, then you get the 3 sphere. For example, if you take a 0 sphere and a 0 sphere, you get a 1 sphere. If you take a 1 sphere and a 0 sphere, you get a 2 sphere. So, but in this case, if you take a 1 sphere and a 1 sphere, you get a 3 sphere. Because this is chromatic number 3, this is chromatic number 3, this is chromatic number 6. But most of the examples, when you look at them in the computer, in most of the cases, when you look at graphs, the chromatic number of spheres is 4 or 5. So that it can be 6 was a little bit a surprise to me. But it's totally obvious once you see this algebraic structure. By the way, the addition of manifolds is not necessarily a manifold anymore. And the reason is because just if you look at the proof, then this is chromatic number 3, this is 4, so for 7. So in this case, you get already for 4 manifolds, you get 7. 4 spheres, you can already have the chromatic number 7. Now the upper bound is for 4 spheres is 10. So 8, 9, 10, we don't know. So for manifolds, it's a little bit different because to have a 4 manifold with chromatic number 7, what you do is you make sure that one of your unit spheres is this. If that unit sphere needs 6 colors, then the manifold needs already 7 colors. So there are 4 manifolds already where you have 4 manifolds where you need 7 colors. We don't know what for 4 manifolds the maximum is. For 4 manifolds we have only an upper bound 10. So it could be 8, it could be 9, it could be 10. It would be extremely interesting to have examples where 4 manifolds, for example, where the chromatic number is 8. Yeah, it got off. Anyway. So maybe I have to talk about this a little bit more in another time, but it's something which hatched pretty shortly after that project in December 2014 or so. I was thinking about how to actually use higher dimensional space to color. And first of all, one of the ideas you can do is you take your graph G, which you want to color, and you make a copy of that graph. So that was the first approach. And you make a cobordism, meaning you're filling it in with a higher dimensional. So you connect it here. So you make something else and you connect it. And then you make this Eulerian. So you make the interior Eulerian by cutting. An edge refinement means you take an edge and you put a new vertex there, and you connect to everything in the intersection of SA intersected with SB. So in this case, when you make this edge refinement, what you get is then you get this has 1, 2, 3, 4, 5, 1, 2, 3. These are both have 5, degree 5, which we don't want. So what you do is you kind of make edge refinements like that. So I take this and color this with 3 colors. So now I have no choice here. I have to put the green here. The yellow goes over here. And now you see it worked. So what we have done is once we have, if you have this Eulerian disk, we can color it. So what happens in higher dimensions, what you want to do is this edge has degree 5, has a degree of that edge degree is 5. Because what happens is the intersection of that unit sphere with that unit sphere is this unit sphere with this unit sphere is a circular graph with 5 vertices, which is odd. Refine this one. So if you refine this one, meaning we make that thing and then we connect everything over like that. I have to use a longer one here. Take this, connect it like that. What you end up with 6 degree 6, and you make it even. So once you have that, once you have an even degree, you can color it. You can color it nicely, and then you can do the same thing. You can take this and flip it on the other side, flip it on the other side, go over and fill out the whole manifold. As long as it's simply connected and this has this Eulerian property. So you want to kind of cut it in such a way so that you make this Eulerian and then you have colored also the boundary. You never cut the boundary because the boundary is not is off limit. So you never touch this. That's kind of something I experimented with in I think summer 2016. An easier approach came later. Why not just color a ball? So that's actually the proof of the 4 color theorem, as I believe it actually works. Still, this is a very treacherous topic. I have to warn so that you can make mistakes. This should give you a polynomial constructive argument. I wanted to see kind of how that actually works with the camera if I take this very, very beautiful sphere. It's a constructive argument, which should be polynomial in the number of vertices. So first of all, what you do is write. That's no problem. We can just take B, for example, you can take B is equal to S with 1 point, right? So if you take that S with K1, that's a ball. Now take a point, then we take, this is the whole thing is B, and that's Bx. So what you want to do is you want to make these edges, first of all you want to make these edges Eulerian. Let's call this U. Edge refine this, call this C. This C is just a 2-dimensional disk here. At every stage this C is a 2-dimensional disk. And what you want to do is you want to have every vertex degree, interior vertex degree in C has to be even. And you do that with edge refinement. For example, you want to make this Eulerian. What you do is you just start cutting. What you have to do is you have to first build a possibility to actually make this change this edge degree. And so now what you can do is you can connect this. Now this edge degree is 6. So this is 6, this is 4, this is 4. Now all edge degrees are even. When this edge degrees is even, this is equivalent that this edge degrees, interior edge degrees are even. What we have is now an Eulerian disk, so everything in that region U is now grow U. Either by extending something here or extending something here. So what we do is we successively change here, make this larger and larger. And for that, that's the reason I got interested in Reep's theorem, because what we need is that we need kind of a strategy to find different points here. So now grow U, but there's a difficulty here. The union of 2 intersecting balls is not necessarily a ball. These parts, there's some kind of like canyons. You make this, you refine it around it to make it a little bit, more spacious, so that you can you can do that. But then you introduce new points. In every extension step, we want to gain one more vertex. Here, what we do is we extend it in such a way that at every stage, we really have a ball here. After every refinement, we have to make again we have to make this membrane Eulerian. That costs us also time. But in every stage, in every step, we gain one vertex, and then we make the Eulerian thing. We gain one vertex, we make it Eulerian. We make one vertex, we make it Eulerian. Once we are finished, every of these circles here has even degree. So this is automatically Eulerian. Now, if the ball is Eulerian, we can color it with 4 colors, and this also colors also original sphere S. And at no point we have touched the sphere S. So it means that we have grown a larger and larger ball, which is Eulerian, until everything is Eulerian, which still needs to be implemented in a computer.